Beneath the roaring winds and icy tempests of the Southern Ocean lies one of the most treacherous waterways on Earth, the Drake Passage, stretching roughly 404 miles, 650 kilometers, between Cape Horn at the southern tip of South America and the northern edge of the Antarctic Peninsula. This vast corridor of ocean serves as the only natural link between the Atlantic and Pacific. It is a place sailors both fear and revere, infamous for monstrous waves, unpredictable currents, and storms that can rise from calm seas in minutes. Named after the English privateer Sir Francis Drake, who crossed these waters in the 16th century, the passage represents both the edge of human endurance and a natural laboratory of immense geological energy. For centuries, explorers have spoken of its wrath, but what lurks beneath this remote expanse is even more formidable, a dynamic, restless sea floor where the forces shaping the planet collide in silence. On October 10, 2025, this hidden tension erupted in violent fashion. At precisely 8:29 p.m. Coordinated Universal Time, the ocean floor of the Drake Passage convulsed with the force of a 7.6 magnitude earthquake, according to the United States Geological Survey, USGS. The quake struck at a shallow depth of about 6.5 miles, 10.5 kilometers, below the surface, shallow enough to transmit its energy efficiently across the water. Its epicenter was pinpointed at 60.3 degrees south latitude and 61.9 degrees west longitude, roughly 436 miles, 702 kilometers, south-southeast of Tolhuin, Argentina, and 438 miles, 705 kilometers, southeast of Ushuaia, the southernmost city on Earth. Initial seismic readings varied, slightly depending on the monitoring station. The European Mediterranean Seismological Center registered a 7.7, while early data from other international agencies estimated up to 7.8 before revisions refined the analysis. Variations like these are routine in large-scale quakes, as sensors scattered across the planet take time to process and synchronize the complex web of seismic waves. Still, every report agreed on one fact. This was a major tectonic event, one capable of unleashing widespread effects across the southern hemisphere. The relief, if any, came from geography. The quake occurred far from densely populated regions, deep in one of the most isolated corners of the planet. Yet proximity to land was close enough to spark serious alarm. Puerto Williams, Chile, a small but vital settlement on the northern coast of Navarino Island, sits roughly 135 miles, 218 kilometers, from the epicenter, making it the nearest human community to the quake's origin. Further north, the regional hub of Punta Arenas, home to more than 117,000 residents, lies about 590 miles, 949 kilometers away. While infrastructure damage in these cities was not immediately evident, scientists feared a secondary danger that often follows such underwater quakes: tsunamis. Just 19 minutes after the quake struck, the Pacific Tsunami Warning Center, PTWC, issued an urgent advisory for the Chilean coast. Their bulletin warned that hazardous tsunami waves were possible within a 1,000-kilometer radius of the epicenter. Forecast models suggested that the first waves could strike Puerto Williams by 6:36 a.m. local time on October 10th, followed by Punta Arenas several hours later, around 2:49 p.m. The rapid issuance of these warnings underscored the speed and precision of modern monitoring systems, vital tools in preventing tragedies across coastal communities. The Hydrographic and Oceanographic Service of the Chilean Navy, SHOA, quickly echoed the alert, urging vigilance across the entire southern coastline. Within minutes, Chile's National Service for Disaster Prevention and Response, CENIPRED, activated emergency evacuation protocols for all communities within the Magallanes region, the country's southernmost territory. Residents were told to immediately move away from beaches and low-lying areas to elevated ground. Sirens wailed through coastal towns as emergency personnel fanned out to guide families to safety. Radio broadcasts and mobile alerts carried the same clear message. The ocean was unpredictable, and every second counted. President Gabriel Boric, a native of Punta Arenas himself, wasted no time in responding. He suspended his schedule and returned to La Moneda Palace in Santiago to oversee the national response. Through social media, Boric urged calm but firm action, reminding citizens that every resource of the Chilean state was mobilized. to confront the threat. Follow evacuation instructions, he wrote. Do not underestimate the sea. His message was amplified across television, radio, and digital networks as Chile's civil defense infrastructure shifted into full emergency mode. On the streets of Punta Arenas, local news cameras captured scenes of urgency mixed with composure. Families carried backpacks filled with essentials, blankets, food, water, documents, as they climbed toward higher ground. Vehicles streamed inland, headlights cutting through the dawn mist as people sought safety. Schools and public buildings on elevated terrain became temporary shelters. Despite the anxiety, the calm coordination reflected a population deeply familiar with living in one of the world's most seismically active nations. Chile has learned, often painfully, that readiness can mean survival. Authorities extended the warning even further south, to Chile's Antarctic research bases. Facilities such as Base Pratt and the O'Higgins Research Station, situated on the Antarctic Peninsula, were ordered to move personnel and scientific equipment to secure locations. Though hundreds of miles away, the unpredictable nature of tsunami propagation meant even these frozen outposts were not beyond potential impact. Scientists stationed there paused their experiments to monitor ocean sensors in real time, a stark reminder that even the most isolated places on Earth are linked by the restless pulse of tectonic forces. Across the border, Argentina also moved swiftly. In Tierra del Fuego, provincial authorities issued precautionary advisories, closing ports and suspending all navigation in the Beagle Channel. The Civil Protection Secretariat halted all aquatic activities and coordinated with the Chilean Navy for joint observation of sea level changes. These actions underscored a vital truth. When nature strikes, cooperation transcends politics. Both nations share not only a border, but also exposure to the same volatile geological systems that have shaped South America's southern frontier for millions of years. The Drake Passage lies at the meeting point of immense tectonic and oceanic forces, where the Scotia Plate, Antarctic Plate, and South American Plate jostle for dominance beneath some of the roughest seas on Earth. It forms part of the Pacific Ring of Fire, a 25,000-mile horseshoe of instability encircling the Pacific Basin. This zone is home to 90% of the planet's earthquakes, and about 3/4 of all active volcanoes. For Chile, earthquakes are not rare occurrences, but an inevitable fact of life, born from the slow, inexorable subduction of the Nazca Plate beneath the South American continent. This process unfolds along the vast Atacama Trench, an underwater scar plunging more than 26,000 feet, 8,000 meters, deep. Every year, the oceanic Nazca Plate creeps eastward at about 2.8 inches, 7 centimeters, forcing its edge beneath the continental crust. The friction builds colossal energy along the fault line, and when that energy releases, the Earth shakes with catastrophic power. The 7.6 event in the Drake Passage is a vivid demonstration of this ongoing planetary engine, one that never truly sleeps. In the hours following the quake, ocean buoys positioned throughout the Southern Ocean detected subtle sea level changes consistent with mild tsunami generation, though no catastrophic surges were confirmed. Chilean naval units deployed reconnaissance aircraft to monitor wave movement, while scientific vessels equipped with sonar systems began assessing the seafloor for signs of rupture or uplift. Though damage to populated areas appeared minimal, the event served as another warning of how fragile the balance between Earth's tectonic plates remains. Geologists are now studying whether this quake may be linked to broader seismic stress transfers along the Antarctic-South American boundary. Some early models suggest the tremor could slightly increase pressure along adjacent fault systems, closer to the Chilean mainland, though the risk remains speculative. Still, each event provides valuable data that helps refine understanding of this volatile region. For the global scientific community, the Drake Passage quake represents both danger and opportunity, a natural experiment in one of the least studied corners of the world. The information gathered from it may improve future tsunami prediction models and help strengthen monitoring networks across the Southern Hemisphere. Natural disasters remind us that even in the age of satellites and supercomputers, the Earth remains unpredictable. What happened beneath the Drake Passage on that October night is not just an isolated tremor. It is a reminder of the forces that shape continents, carve mountains, and command the seas. Humanity can measure and prepare, but it cannot control. If you found this report compelling and want to stay informed about the latest in geology, volcanology, and seismic events, make sure to subscribe and enable notifications so you never miss an update. Share your experiences in the comments below. Whether you've lived through an earthquake, a tsunami warning, or any natural event that changed your perspective, together awareness and knowledge can turn fear into preparation and preparation into resilience. Sicily's towering fire mountain looms over the island's east like a restless cathedral. Mount Etna in southern Italy is not only large by European standards, it is the continent's most energetic volcano, a place where the crust moves and sometimes roars. Its summit stands near 10,825 feet, about 3,300 meters, though the exact number shifts with each outburst as craters build and collapse. For centuries, Etna has cycled through eruptions and pauses, becoming both a research site and a major attraction. That appeal comes with a sober reality. Beauty and danger share the same slope. Etna's behavior does not follow one simple script. It moves along a spectrum, from modest Strombolian pops and ash puffs to short, intense episodes that fling columns of molten rock skyward. In the latest chapter, fresh lava has again threaded down the flanks, cutting glowing rivers through black scoria, while orange fountains light the night. Authorities tightened access, keeping people below roughly 8,200 feet, about 2,500 meters, while instruments flagged elevated shaking. The goal is straightforward: admire the show, but keep distance while the mountain's pulse is high. A new feature has become the focal point of concern, a visible fissure on the upper slope. Drone surveys and handheld footage make the crack unmistakable. This is not a surface blemish. Fractures like this reflect underground stress as pressurized magma pries rock apart. Such openings can precede larger events, lateral eruptions lower on the cone, or in more severe cases, structural slumps that peel away portions of the flank. Scientists have long measured a slow, persistent slide of parts of Etna seaward, a creep that usually proceeds at a walking pace each year, but hints at the forces at work inside the edifice. In rare cases elsewhere, sudden volcanic slope failures have even kicked up waves. That is not a forecast for Sicily, but it explains why a new crack instantly raises the stakes for monitoring. Even as lava fountains and glowing streams seize the eye, the volcano's internal heartbeat, the tremor signal, continues. It strengthens and dips, but together with surface deformation, it points to a system under pressure. Volcanologists are asking a simple question with complicated implications. Is this a familiar pulse in Etna's rhythm, or the start of a deeper reshaping of the mountain's plumbing and flanks? The fracture sits just below the summit crater complex, in what specialists call a subterminal zone, near the 3,000-meter contour. That belt is notorious among Etna watchers, because stress can accumulate there until the volcano chooses a side vent instead of the summit. Flank eruptions are disruptive. They can open abruptly, cross trails and roads, and send lava toward valleys long unused to flows. Their unpredictability raises risk for hikers, workers, and nearby communities alike. Ground sensors show deformation consistent with magma intrusion, hot material wedging into cracks and lifting the surface. Biomount satellites detect even when people notice nothing. The new fissure is likely the surface expression of that push. If intrusion continues, modest activity can escalate into stronger paroxysms, or if rock fails, into local collapses. Recent aerial passes mapped several small vents feeding multiple lava tongues. As they descended, the flows split and rejoined like braids in a river. The farthest fronts reached about 7,546 feet, around 2,300 meters. Higher up, the summit vents above, roughly 9,843 feet, near 3,000 meters, continued to supply fresh magma, turning the upper slopes into a moving assembly line of incandescent rock. In parallel, Italian civil protection raised the alert posture. An F1 advisory signals heightened caution and keeps the summit effectively off limits. Should conditions escalate to an F2 stance, as happened earlier this season, authorities would warn about fast-moving hot clouds and sudden hazards. A recent dip in seismic chatter may look like relief, but lulls on Etna often precede bursts. Paroxysmal episodes, sudden violent releases of pressure, can drive sky-high lava jets, loft tall ash plumes, and blast glowing class across wide arcs. Those class, called lapilli volcanic bombs, can be as small as gravel or as large as a football, and they travel fast. On busy volcanoes worldwide, people have been injured by projectiles and ash clouds that outran expectations. A grim lesson from New Zealand's Wakari/White Island is that a volcano in routine activity can still switch gears without much warning. Etna is more active than most, so that lesson applies doubly here. Part of the management challenge is Etna's shape-shifting tempo. A cycle can start with tame spattering, leap into fountains, toss short-lived pyroclastic surges, then fall back to a simmer. The newly mapped fracture could mark a deviation from that familiar arc, hinting that structural stress is accumulating in a way that increases the odds of a lateral opening. Italy's National Institute of Geophysics and Volcanology reports ongoing strombolian bursts at the summit with intermittent ash visible from surrounding towns. Analysts watch more than camera images. They track the precise height of advancing lava fronts, monitor the rise and fall of harmonic tremor, and listen for infrasound signatures that reveal explosions even when weather hides the vents. Together, those metrics show magma still moving underground and feeding the surface. Because the system is unsettled, caution is wise. No one can say with confidence how the next day or two will unfold, and that uncertainty is itself a warning sign. Persistent tremor, active deformation, a fresh fissure, and multiple lava sources argue for restraint on the mountain and vigilance in the communities below. A new vent can open with little notice. An existing vent can choke and then clear with more force. Wind can swing an ash plume over a road that was clear an hour earlier. Sicilians have lived with that reality for generations. Ash on the windshield at breakfast and a faint glow on the horizon after sunset are part of the local rhythm. When instruments show rising risk, authorities close trails and restrict access. The latest fracture, together with pressure signals, argues for a stretch of heightened respect. Being prepared, knowing routes, keeping masks, having a communication plan is not alarmist. It is responsible. Round-the-clock monitoring continues. Networks of seismometers listen for swarms, too small for people to feel. GPS receivers and tilt meters register millimeter-scale motions of the ground. Thermal cameras chart the heat of flows and vents. Gas sensors measure sulfur dioxide and other emissions that rise when new magma nears the surface. Drones supply overhead views that ground teams cannot get safely. Together, these tools give a near real-time portrait of Etna's mood and help officials adjust closures and guidance. The broader scientific community follows closely because each Etna cycle teaches lessons that travel. Comparing data from Sicily with other regions sharpens models of magma ascent, flank stability, and the thresholds that tip a photogenic eruption into a hazardous one. In that sense, every measurement taken on Etna contributes to the global understanding of how our planet moves heat and material from its depths to the surface. For visitors and locals, the advice remains simple. Enjoy the spectacle from safe lookouts and respect guidance from the park and civil protection. Keep clear of summit zones. While the alert is elevated, the mountain's beauty is real, and so is its unpredictability. Respecting both is how you witness the show, without becoming part of the response. If you're passionate about geology and want more updates as this sequence evolves, stay tuned. We'll keep translating measurements and field notes into plain language. Share your thoughts below. Do you think this fissure signals a larger shift, or will Etna settle back into its familiar cadence? Your perspective helps guide what we explain next, and your caution helps keep everyone safe on the slopes. Quick glossary. Strombolian means rhythmic bursts from gas bubbles at the vent, spectacular but typically limited in range. A paroxysm is a short, powerful peak that can hurl lava high and spread ash widely. Pyroclastic flows are fast, ground-hugging clouds of hot gas, ash, and rock. Rare on Etna, but dangerous enough to drive higher alerts. Lapilli are small cinders. Volcanic bombs are larger blobs that harden in flight. Terms like these explain why rules can change quickly. Last point, volcano science is probabilistic, not prophetic. Analysts merge many weak signals, small gas shifts, subtle tremor, centimeters of tilt, into a picture of rising or falling risk, then revise it as new data arrive. Patience with restrictions and respect for the mountain make safer outcomes possible. Stay informed, stay flexible, and give Etna space. Roughly 311 miles, about 500 kilometers west of Oregon's shoreline, far below the gray swells of the Pacific. A hidden volcano rises from the abyssal plain. This undersea mountain, called Axial Seamount, sits squarely along the fiery backbone of the Pacific Ring of Fire, the vast horseshoe of faults and volcanoes that girdles the ocean. The Pacific Northwest is no stranger to restless geology. It is home to the Cascades and to infamous peaks like Mount St. Helens, whose 1980 blast still serves as a cautionary tale. The story stretches back millions of years to when the Pacific Plate began diving beneath North America. That slow-motion collision helped build the Cascade Arc from Northern California into British Columbia, and it also set the stage for submarine giants like Axial. From the seafloor, it climbs like a dark cathedral, its summit still roughly 5,249 feet, about 1,600 meters, beneath the sea surface. Lately, something unusual has been stirring down there. In a single day, instruments recorded more than 300 earthquakes around Axial, a spasm of motion that is far from routine. The pattern of shaking has scientists on high alert because it resembles the run-up to the seamount's previous eruptive episodes. One veteran oceanographer put the risk in stark terms. If this were happening beneath a town rather than beneath thousands of feet of water, emergency managers would already be clearing neighborhoods and putting evacuation plans into motion. The Pacific may look calm from a ferry deck. The forces below are anything but. So what's driving this drumbeat of quakes? The best explanation points to magma creeping upward through fractures in the oceanic crust. As molten rock pushes into the plumbing system beneath the summit, it pressurizes the volcanic edifice. Think of a balloon being slowly inflated inside a rigid box. At some point, the pressure has to find release. When that moment comes, the seafloor can split, lava can pour out, and the volcano can undergo an eruption, measured not in towering ash plumes, but in rivers of basalt that harden into black glass on contact with cold seawater. The year 2025 has already delivered several eyebrow-raising bursts of activity. In June, instruments tallied an astonishing flurry, more than 2,000 earthquakes in just 24 hours. That spike eventually eased, settling back to roughly 100 tremors per day for a time, but counts have again climbed into the hundreds. Even without any one massive jolt, the sheer persistence of these tiny quakes is a red flag. To grasp the scale, remember what happened the last time Axial really let loose. During the April 2015 event, over 8,000 earthquakes were logged in a single day. That is the tempo of a volcano in full swing. Today's numbers are lower, but the trend line and the style of the signals echo that run-up. And that is why researchers are treating the present sequence as more than a curiosity. A second, equally troubling clue is showing up in the shape of the volcano itself. Axial appears to be inflating, its surface subtly lifting as new magma collects in a reservoir beneath the summit. Before the 2015 eruption, that ballooning reached a notable threshold, and measurements now suggest the edifice has swelled back to similar levels. The tempo of uplift has accelerated too. Whereas typical years saw the ground rise on the order of 2 to 4 inches, roughly 5 to 10 centimeters, the rate jumped dramatically beginning in January 2024. By July, some stations near the center of the caldera had captured as much as 6 inches, about 15 centimeters, of cumulative uplift, and peak pockets were pushing toward 10 inches, around 25 centimeters. That's a remarkable amount of motion for rock to undergo in such a short interval, and it fits uncomfortably well with the surge in microquakes. Both are classic symptoms of a magmatic system under pressure. All of this is unfolding inside a volcano with serious dimensions. Axial is not a neat cone. It's a sprawling complex capped by a caldera and rift zones that stretch for miles along the seafloor. The main magma storage zone sits around 2,625 feet, about 800 meters, beneath the top of the edifice, a sizable chamber of molten rock feeding the system. Although its summit remains more than 1,000 meters below the ocean's surface, which muffles direct effects on coastal communities, there is nothing small about the forces at work. For volcanologists, Axial is both a laboratory and a test. Here's a system we can watch closely. one that erupts often enough to study modern processes in real time, and one that can teach us about the rhythms of more dangerous volcanoes on land. Predicting eruptions is notoriously difficult, but Axial may be giving scientists the best shot yet at a well-timed forecast. The volcano has a quirky personality. Periods of rapid inflation can be followed by quiet plateaus, then by renewed surges. But the current combination of inflation, seismicity, and the sheer pace of change has led some researchers to a striking conclusion. Odds favor an eruption before the end of 2025, possibly at any time. That doesn't mean a cataclysm is guaranteed, and the ocean will absorb much of the spectacle. Yet from a scientific standpoint, capturing such an event with modern eyes could be historic. That's because the monitoring toolkit on site is far better now than in previous cycles. A sophisticated network of cables, junction boxes, and sensors sits on and around the caldera, streaming data continuously. Tilt meters watch the ground breathe. Pressure gauges register tiny changes in the overlying water column. Seismometers listen for the crackle of moving magma and the pop of breaking rock. Some nodes are tied into cameras and chemical sensors, ready to catch visual signs, plumes of shimmering water, sudden turbidity, or hydrothermal fluid bursts, should the seafloor split. Instead of occasional research cruises, stitching together snapshots weeks or months apart, scientists now have a live feed from the deep, second by second. If Axial opens a new fissure, that system could record the sequence with a level of detail never achieved for a submarine eruption. The earthquakes being tallied are not large in the way the public imagines earthquakes. Most cluster around magnitude 1 to 2. But in a volcanic setting, that's exactly what you'd expect. Swarms of small events that collectively map the path of magma as it wedges itself into cracks. Each tiny quake is a stress whisper, a brittle fracture here, a slip there, a local pressure drop, followed by renewed push. The pattern matters more than any single number. A broadening swarm, increasing rates, a change in the dominant depths. These are the signatures forecasters watch, and recently those signatures have been trending in the direction of unrest. It's worth emphasizing that undersea eruptions differ profoundly from those on land. There will be no ash cloud blotting out the sun, no red fountain visible from coastal highways. The pressure of 1,000 meters of seawater forces lava to quench instantly into jagged pillow shapes, piling up like toothpaste squeezed into ice water. Still, the consequences can be significant. New lava can dam or reroute hydrothermal circulation, altering ecosystems. Seafloor topography can change over days. In some cases, gas release or rapid heating can drive local hazards at the surface, though at Axial's depth, the ocean generally dampens such effects. For ships and nearby infrastructure, the main risks would be to subsea floor cables and instruments, not to ports and cities. Even so, studying Axial is not an academic luxury. The physics of magma moving through rock are universal. Lessons learned here, inflation thresholds, the relationship between seismic swarms and dike intrusions, the way pressure migrates through a branching rift network, translate to stratovolcanoes that do loom over towns and highways. Every data point from Axial sharpens our playbook for hazards on land. If researchers can validate a reliable chain of precursors at this seamount and peg the timing of an eruption within a meaningful window, it would represent a milestone for eruption forecasting writ large. None of this erases the reality that volcanoes can faint. Axial's history includes stretches of rapid uplift that stall, intervals where quakes scatter then regroup, and episodes where magma intrudes along a rift without breaking the surface. Forecasts must dance with uncertainty, but uncertainty is not ignorance, and it is not paralysis. It is a quantified range, narrowed by each new sensor, each fresh data set, each additional hour of continuous monitoring. Right now, the picture looks like this. The volcano has reinflated to levels comparable to those seen before the 2015 eruption. The rate of inflation accelerated markedly, beginning in early 2024. Earthquake counts surged to extraordinary highs in June 2025, and continue at elevated levels measured in the hundreds per day. And the overall behavior suggests a pressurized system. The simplest interpretation is that magma is on the move and that the system is trending toward a release. If and when that release happens, the sequence is likely to unfold rapidly. A dike, a blade-like body of magma, could propagate along one of Axial's rift zones, opening a fissure on the seafloor. Seismicity would spike, then reorganize into a migrating front as the intrusion advances. Tilt meters might register sudden steps. Pressure sensors could show subtle changes as warm fluids pulse outward. Cameras, if lucky enough to be pointed in the right direction, might catch the water clouding and shimmering. Lava would extrude and cool into lobate pillows, building new crusts, even as the underlying reservoir deflates and the ground above sags. After days to weeks, the system would quiet, leaving behind a freshly minted patch of ocean floor and a trove of measurements for scientists to decode. For now, the best course is vigilance. The deep ocean network continues to hum, logging every tremor, every millimeter of rise or fall. Research vessels stand ready to sail when weather windows open. To ground truth, the signals with plume sampling and high-resolution mapping. And the public, though insulated by distance and depth, can take real comfort in the fact that this is a volcano we can watch in detail, one whose behavior is teaching us how to read the signs at other, more immediately consequential volcanoes around the world. Curiosity about Earth's hidden machinery is more than a hobby. It's a form of preparedness. The more we understand how magma moves, how rock responds, and how seafloor systems breathe, the better we can anticipate the next chapter, underwater at Axial, or atop a mountain closer to home. If this kind of deep time detective work fascinates you, stay tuned. We'll keep translating the pulses of the planet into stories you can see and understand, as this undersea giant writes its next line in the Pacific's long volcanic script.